Okay student, in this video I'm going to explain about the energy stored in a capacitor. As all you know that capacitor is like a water tank in which a tank, it is used to store a water. So similarly a capacitor is used to store a charge. Now this is my capacitor, which consists of two plates, and I'm connecting it to a source of energy in this way. So this source here which will supply a charge to the capacitor, and as you are giving charge to the capacitor, then the charge should be transferred from one plate to another plate. Okay, so this process of charging a capacitor, it involves a transferring of charge from one plate to another plate. So in this case the work done to store the charge in the work done to charge the capacitor, it is stored in the capacitor as the electric potential energy. Now let us see about the expressions of the energy stored in the capacitor. So as you can see here, this is a capacitor which is connected to the source of energy, and let's say this capacitor is having a capacitance C. Suppose at any instance of time the charge given to the capacitor, let's say it is Q dash, and the potential difference between the plates of the capacitor, let's say it is V dash. So therefore I can write capacitance here is equals to Q dash by V dash. Now if a small charge dq, it is further transfer from positive plate to the negative plate, then small amount of work done has to be done, and that amount of work done is dW, and this dW is given as V dash dq dash, or we can say dW is equals to, instead of V dash, look at this, you can write Q dash upon C times dq dash. So this is a small work done to store a charge, this is the small work done to charge the capacitor, or when a charge dq dash is given to the capacitor, this is the amount of work done. Now the total work done to give a charge Q to the capacitor can be obtained by integrating this equation 1. Now if you integrate this equation 1, integration of dW, it will be W, and now if you integrate this, you will get integration, let's say from 0 charge up to Q, it is Q dash upon C and then dq dash, or we can say W is equals to, since C is common here, I will take it outside, and you integrate only from 0 to Q of Q dash dq dash. Okay, so as you know, integrations of x dx is equals to x square. So similarly integrations of Q dash dq dash will be Q dash square, and the limits of integration is from 0 to Q. Now substituting the limits of integration, you will get 1 upon C. Instead of this Q dash, the upper limit is Q, so I'll write Q square. Lower limit is 0, so instead of Q dash I'll put 0 square. So this total work done now becomes 1 upon C Q square. Okay. Okay, I think I missed out a factor 2 here. So because integrations of x dx is x squared upon 2, so when you integrate this q dash dq dash, it will be q dash upon 2. So now I'll take this 2 out, so everything will be the same. Substituting the upper limit and lower limit, you'll get this much. Okay, so this work done is nothing but it is the energy which is stored in the capacitor. So therefore I will write the electric potential energy that is stored in the capacitor is U equal half Q1 upon 2 C Q square, or I can say this is equivalent to 1 upon 2. This is C instead of Q, because you know C is equals to, Q is equals to CV. So instead of Q I will write CV. So if you write that, you'll get C square V square over here. So this with this cancels, you'll get half CV square. Okay? Or again, in place of C, in place of this C, I can write from here Q upon V times Q square. So this square with this Q cancels, you'll have 1 upon 2. This V take up, it becomes QV. Okay, so this is the expressions of the electric potential energy stored in a capacitor. So in order to memorize this formula, I will write like 1 upon 2 CQ square, which is the first expression. Next 1 upon 2 CP square. Next half QV. So these are all the 3 expressions of electric potential energy stored in a capacitor.